Hello everyone, I'm Fabian Dedeker from Itasca, France. Thank you for joining this new webinar on our software applications. This new webinar will be presented by Professor Vasilis Sarhosis from the University of Leeds, who is a UDEC and 3DEC user for many years. He will be presenting you his works on discrete element modeling of Masonry structures.
Good evening. I hope you are all safe and healthy during these difficult times. My sympathy and support is with those affected by the COVID-19 virus. I would like to thank Itasca for giving me the opportunity to present my research on modeling masonry structures using the discrete element method. My name is Vasilis Sarhosis. I'm an associate professor in structural engineering at the University of Leeds. Also, I'm a chartered engineer and a fellow of the Higher Education Academy in UK. Currently, I'm chairing the National Scientific Committee on the Analysis and Restoration of Structures of Architectural Heritage, which is part of ICOMOS. My principal research interests are in understanding the mechanical behavior of old and deteriorated masonry structures and provide detailed and accurate data that will better inform maintenance programs and asset management decisions. In this webinar, I will discuss 4 different examples of my past research on modeling masonry structures using DEM. The assumptions adopted by these models and numerical implementation issues will be outlined. At the end, I will conclude with some future trends for modeling masonry structures using DEM. But let's first discuss on the mechanical behavior of masonry. Masonry is a composite material consisting of masonry units bonded together with or without mortar. Although masonry is very easy to construct, its mechanical behavior is nonlinear and thus complex to predict. Masonry is very weak in tension and very strong in compression. In fact, mortar joints act as plane of weakness in masonry. The need to predict the in-service and load carrying capacity has led to the development of computational strategies which are characterized by different levels of complexity. Such models range from considering masonry as an anisotropic continuum, the macromodeling approach, to the more detailed ones considering masonry as an assemblage of units and mortar joints, the micromodeling approach. Now, since old and deteriorated masonry structures are typically characterized by low bond strength, cracking is often a result of the debonding of the masonry units from the mortar joints. Given the importance of the masonry unit to mortar interface on the structural behavior of aged masonry structures, micromodeling approaches, i.e. those based on discrete element method, are better adopted to simulate the serviceability and load carrying capacity of such structures. The discrete, or otherwise called distinct element method, developed by Peter Kandel in the early 70s to model sliding rock masses in which failure occurs at the interface. More recently, the method has been successfully used to model masonry structures in which the failure mechanism is governed primarily by the masonry unit mortar interface characteristics. DEM has been implemented in UDEC and 3DEC software, which were developed by Itasca. The first example relates to discrete element modeling of masonry in compression. Masonry structures are often subjected in compressive loads. For example, the picture in this slide shows an over 100 years old brick masonry viaduct located in UK. Over the last years, the masonry arch bridges and viaducts were subjected to higher and more frequent cyclic load, resulting in premature cracking and deterioration. Therefore, it is vital to understand their in-service and load-carrying capacity. It is well known that when mortar is weaker than the strength of the bricks, then the bricks are subjected to bilateral tension and the mortar in a triaxial compression. The failure mechanism of a masonry prism subjected in compression is characterized by vertical cracking. Therefore, in order to accurately model the compressive strength of masonry, the numerical model should allow a reliable estimation of the masonry compressive strength and failure pattern. However, the current available models based on macro and micro modeling are able to represent masonry failure in a phenomenological manner. In this way, the quasi-brittle behavior of masonry cannot be simulated. Similarly, current developed computational models based on DEM are able to represent failure at the brick-mortar interface or mortar itself rather than the bricks. In this study, an alternative approach for modeling the discrete nature of masonry subjected to direct compression has been developed. In the proposed modeling approach, the microstructure of masonry units and mortar was modeled as an assemblage of densely packed, irregular in shape and size discrete elements bonded together by a zero-thickness interface. Such irregular elements could be a few millimeters in size and are able to move independently to each other, open, close, or slide. In this way, cracking can be allowed in either brick-mortar and/or brick-mortar interface. Inner block can be subdivided into simple triangular finite elements, designated as zones, which give a much better approximation of the strain field than the assumption of uniform strain in the whole inner block. In this example, the discrete deformable inner block elements containing internal mesing are assumed elastic, but a nonlinear material behavior may also be used if necessary. In the numerical model, inner blocks are connected together by point contacts. At each contact, there are two springs which can transfer a normal and shear force. At the contact, if the tensile strength defined by the user exceeds the normal stress, then the normal stress becomes zero. Similarly, in the shear direction, slippage between blocks occurs when the tangential or shear stress at the contact exceeds a critical value Tmax defined by C plus normal stress tan phi, where phi is the angle of friction and C the cohesive strength. After the slip takes place, the shear stress is reduced according to the Moore-Kulob criterion, but using residual values for cohesion and friction. Non-associative flow rules can be applied. Therefore, the dilation angle psi is set to zero. After a contact breaks or slips, forces are distributed and it might cause adjacent contacts to break. A numerical model has been developed to simulate the direct compression of a masonry prism tested in the laboratory by Oliveira in 2003. The masonry prism was composed of 5 bricks. The bricks had average dimensions of 290 mm by 130 mm by 50 mm. Joints were all made of cement mortar and had thickness equal to 10 mm. The prism placed between two steel platters and subjected to an external control displacement until failure. In the numerical model, platters were modeled as rigid blocks. Bricks and mortar were discretized into inner particles and modeled as deformable elements. A low velocity applied at the top of the platter to confirm a quasi-static condition. Vertical load estimated using FIS programming implemented in UDEC. From the numerical simulations, it was observed that the peak appears to take place when one of the bricks splits in two by coalescence of the vertical tensile cracks that progressively develop. Total failure followed when the resisting core started to break. The proposed computational approach shows significant advantages when compared to standard continuum models, since it allows one to observe crack initiation and propagation in a realistic manner. In particular, the approach allows one to model cracking as a real discontinuity among particles and not as a modification in the material parameters. Further details about this model can be found in Sarhosis and Lemos 2018. A similar computational approach has also been adopted to simulate the shear and direct tensile strength tests. Since in this case failure occurs in the mortar rather than bricks, only the mortar have been discretized into inner mortar particles. As we can see from the simulation of the shear strength test, failure occurred at the brick-to-mortar interface followed by a diagonal crack at the mortar itself. Also, in the direct tensile strength test, depending on the properties of the inner mortar particles and brick-to-mortar interface, you can have failure at the brick-to-mortar interface or to the mortar itself. In the second example, we present solid structure interaction phenomena in masonry arch bridges by models developed by DEM. In this particular case, we have simulated the load carrying capacity of the Presswood Bridge located in Staffordshire, UK. The bridge had a span of 6.5 meters and a rise of almost 1.5 meters. The barrel vault, which was a single ring of bricks, had a thickness of 200 millimeters, actually 220 millimeters. The width of the bridge was 3.8 meters. Geometric models to represent the geometry of the Presswood Bridge were created in the Discrete Element software UDEC. The developed 2D numerical model simulates plane strain conditions. Masonry units in the arch were represented by an assembly of rectangular deformable blocks. Mortar joints were represented by a zero-thickness interface. These interfaces can be viewed as interactions between the blocks and are governed by appropriate stress displacement constitutive laws. The discontinuous nature of backfill was represented by a series of irregular in shape particles of polygonal Voronoi-shape elements. Such fictitious irregular deformable particles, here named inner backfill particles, are shown in figure on the right. Inner backfill particles were connected together by zero-thickness interfaces, which can be viewed as the location where mechanical interaction between the inner backfill particles takes place and could be potential fracture or slip lines. The inner backfill particles were simulated as elastoplastic material in this case, while the interaction with each other was covered by Coulomb friction law. The size of Voronoi elements varied from 5 to 30 cm. A good agreement between the experimental and the numerical results was obtained, demonstrating the huge potential of this modeling approach proposed herein. The Voronoi models have the advantage of naturally modeling shear crack initiation and propagation as a real discontinuity between solid particles. However, further research is required to be carried out and investigate methodologies used for the calibration of the interface material properties between the inner soil elements and how such microparameters affect the global behavior of the bridge. The third example relates to the stochastic strength prediction of masonry structures. As already mentioned, today there are several computational models to predict the mechanical behavior of masonry structures subjected to external loading. Such models require the input of material parameters to describe the mechanical behavior and strength of masonry constructions. Masonry material properties are characterized by inherent variability, and this is due to composition and quality of materials, workmanship, curing effects, weathering, etc. However, today engineers are assigning the same material properties throughout the structure to be analyzed. In this research, we propose the development of a DEM model for masonry able to consider the stochastic variability of masonry material properties and investigate how these affect the load carrying capacity of masonry structures. A geometric model of a masonry wall panel with 2 meters opening subjected to in-plane vertical load at mid-span tested in the laboratory was created in UDEC. The developed model is based on the simplified micromodeling approach, i.e., each brick was represented by a deformable block separated by a zero-thickness interface at its mortar bend and perpet joint. The mortar joints were modeled using elastic, perfectly plastic Coulomb slip joint area contact option. In the present work, a probability distribution of the material parameters for the masonry constitutive model has been considered. The mean values and the coefficient of variance for the masonry units and mortar were used to define the material parameters in the model. In particular, the realization of the material parameters was randomly assigned to every brick and mortar joint as shown in figure on the bottom right-hand side corner. To achieve confidence with statistical results, 300 simulations were created. The computational time for the 300 simulations was 48 hours. Monte Carlo type of analyses were performed and the effect of variation of masonry material properties in the masonry wall panel with respect to ultimate load carrying capacity determined. The little peaks in the load against displacement curve shown in the top left-hand side represent relaxation of the loading and moment redistribution in the panel due to the formation of a new crack. When a crack propagates, there is an abrupt loss of stiffness in the panel. The failure mode of the masonry wall panel has also been investigated and compared with experimental findings. Both experimental and computational results showed that there were 4 notable aspects of mechanical behavior in the masonry wall panel, namely, first, initial flexural cracking in the soffit of the panel. Secondly, development of flexural cracks in the base joint of each support. Third, propagation of diagonal step cracks at mid-depth. Finally, 4, collapse as a result of what is usually referred as shear failure or excessive diagonal tension. The sensitivity of the elastic and strength parameters on the ultimate load are shown here. The ultimate load bearing capacity is significantly influenced from the mortar strength parameters, i.e. tensile strength and cohesion of mortar, while, as expected, the effect of brick and mortar elastic properties has less significant effect on it. Moreover, for the investigated range of strength parameters, the connection between the ultimate load and the cohesive and tensile strength appears to be linear. It is worth noting that a variation of 10% in the friction angle in a masonry wall panel can vary the ultimate load by up to 55%. The fourth example is discussing the self-supporting spiral staircases. With this example, I would like to highlight how novel structural analysis tools that extend traditional methods such as DEM could assist engineers to understand the mechanisms that have allowed the surviving structures to avoid structural collapse. It is well known that the safety of masonry structures mainly depends upon their geometry rather than strength of material. Rules of thumb adopted in the past for erecting masonry buildings and cathedrals passed on between bricklayers for centuries. In particular, the analysis of helical vaulted staircases is even more challenging due to their complicated geometry. In this research, DEM has been applied to study the statics of different in height helical staircases. This research is under development. However, I'm happy to share with you some initial results. In this case, three different in height spiral staircases investigated using 3DEC. The response of the structures investigated with a view to identify stress distribution and their equilibrium condition. An issue with such staircases is that each step is simply supported and self-supported. Therefore, if you have spiral with many stairs, the last stair is carrying the load from the stairs above. If that was true, then the last stair would not carry the load from above and fracture or fail. However, in reality, this is not the case. From our analysis, it was shown that the normal strength in the last stair in a spiral staircase is no more than 15 megapascal, which is way lower than the compressive strength of stone, which is more or less 30 to 40 megapascal. At this point, I would like to conclude the webinar with some future trends. Over the last years, together with colleagues from Newcastle University, we have developed a web and mobile-based platform called SOC, Save Our Cultural Heritage. The platform allows citizens to upload photographs and or point clouds and develop 3D geometric models of structures. In this example, you see the 3D geometric model of Caerphilly Castle, which is one of the largest castles in Europe and constructed in the 13th century. Such models have been developed using terrestrial laser scanning data. Together with colleagues, I'm currently working on how to make best use of data obtained from photogrammetry and/or laser scanning and develop numerical models of complex in geometry masonry structures. In this example, we have used data from a terrestrial laser scanning survey and developed both FEM and DEM structural analysis models of the southwest leaning tower of Caerphilly Castle. The tower is 17 meters tall and is made of rubble masonry. It is reported to have been leaning for several centuries and stands at a current angle of approximately 10 degrees of vertical. The models were able to provide information related to the limiting inclination angle before collapse as well as understand the potential failure mode of the tower. From the results analysis, it was shown that the automated procedure proposed herein can be effectively used to assess the three-dimensional mechanical behavior of the tower and provide valuable information to asset owners in relation to the structural health condition of assets in their care. Over the last years, together with my collaborators, we have produced a series of research publications on masonry structures modeled with DEM. The most important of them are shown here. Also, together with Professor Lemos, Professor Baggi, and Professor Milani, we have recently published a book on computational modeling of masonry structures using DEM. At this stage, I would like to thank the below people who contributed to the research, as well as greatly acknowledge the financial support of several national and international funding bodies.
Thank you, Vasilis, for this very interesting presentation, and thank you all for attending this webinar. We hope you enjoyed the presentation and that it opened your mind to the possibilities offered by UDEC and 3DEC to model masonry structures. Please do not hesitate to contact Vasily and myself if you have any question. We will do our best to reply you as soon as possible. We wish you all a good afternoon, and at this very special time, we invite you to take care of yourself and your relatives.